Hi, this is Mrs. Basin, and today we're going to learn how to do heat calculations. So when we're doing these heat calculations, remember that Q represents heat. So when it's asking for heat absorbed or heat released, that's going to be Q. That's what you would be solving for. When we do these calculations, the heat is going to be measured in joules because of the unit that we're using for the specific heat, which we'll get to in a second. Now, sometimes afterwards you might have to convert them to something else, but this first set of problems that you're going to work through, you'll be able to leave it in joules. From M, that stands for the mass in grams of the substance that you're investigating. C is the specific heat. Specific heat we talked about yesterday is the amount of heat required to change 1 gram of a substance by 1 degree Celsius. So it's how much heat is necessary for 1 gram of whatever that substance is to increase its temperature by 1 degree. Now, when you look up specific heat values, if you go to look these up online, there's a lot of different tables that have a lot of different units associated with them. So if you are looking these up, make sure that the table that you're using has the units of joules per gram degrees Celsius, because that's what we're going to use when we do these calculations. If you happen to use something else, then you would have to do some other conversions to get it all to work. So for now, let's just use the joules per gram degrees Celsius. And then the final thing that we'll need to know is the change in temperature. When you calculate a delta T, or a change in temperature, you always take final minus initial. This is going to be really, really important, because when we're doing these calculations, when we solve for Q, if you remember yesterday, we talked about Q being either exothermic or endothermic. So if you have a negative Q value, that tells you that this is an exothermic reaction. And if you have a positive Q, that tells you this is an endothermic reaction. So if you don't calculate the change in temperature correctly, that could potentially mess up that sign of Q. So you got to make sure you always do final minus initial. The other thing, while we're looking at this page, one of the things that we're going to use a lot, probably more often than anything else, is the specific heat of water. So liquid water has a specific heat of 4.18 joules per gram degree Celsius. So anytime you have a reaction that's happening in water, then that's going to be the specific heat of that substance. And you'll see that in just a few minutes on this next couple of pages. Okay, so here's another visual. So this shows us the Q equals MC delta T. Q again is heat in joules. M is mass in grams. C is specific heat capacity, and that either depends on the type of substance or the state of the substance. For now, it's going to depend more on the type, and then once we move forward later on this week, it'll depend more on the state. But again, when you're using specific heat, if you're not solving for specific heat, then specific heat would have to be given to you. So that is something that is a constant for different substances. And then finally, delta T is your change in temperature, and we're going to use change in temperature 4 degrees Celsius. So when we work through these, there are 3 main types of these Q equals MC delta T problems that we're going to work through. We'll do an example of each type. And then the first set of practice that you have, they're pretty well split up so that you should be able to tell the difference between them. And then after we've worked through that first practice, then we'll move on to one that's a little higher level, a little more challenging. So for this first type, what we're looking at is heating a single substance. So when you heat a single substance, all you really need is this Q equals MC delta T. Okay, so for this one, when you set these up, even though I know most of you could just plug these into your calculators, what I would like for you to do is to make your list of variables like we've done in the past. And then as you read through the problem, you're going to fill that in, and then that'll make it very clear as to what you're trying to solve for. So for this one, I want to know what is the specific heat of aluminum. So that means C is what I'm going to be solving for. The temperature of a 28.4 gram sample, so that's my mass of aluminum, is increased by 8.1 degrees Celsius. So if they didn't give me a final and an initial, or an initial and a final temperature, and they just told me the difference, that means that's my temperature change. So it went up by 8.1 degrees Celsius. And then I'm adding 207 joules of heat. Okay, and then that you also have to be careful with the sign of Q. So if it says I'm adding heat, that means that that's a positive 207 joules. If it had said that it released that much heat, then that would make that value negative. Okay, so now that I have all of these set up, I have Q equals mc delta T. So Q is 207 joules. My mass is 28.4 grams. C is what I'm solving for, and my delta T is 8.1 degrees Celsius. Okay, so math is pretty simple on this. I'm going to divide both sides by 28.4 times 8.1, and that's going to leave me with my C value. Now, if you notice on this, I have joules, grams, and degrees Celsius. So none of those units are going to cancel, and that's what's going to give me my unit for specific heat. So I should end up with 0.90. I have 2 sig figs here as my lowest, so that's what I'm going to round to. And then I would have joules per gram degrees Celsius, which is the unit that we're going to be using for specific heat. So this tells me that this is my specific heat of aluminum. Another thing you could do is if you don't know what the substance is, that specific heat can actually identify what the substance is. If you didn't know that was aluminum, you could go to a chart and look that up, and you could figure out that that was aluminum from there. Okay, this is the second type of Q equals mc delta T problems you could see. This happens when you're dissolving something in water. Okay, so this is going to be set up a little bit different. So when you're dissolving something in water, there's actually a transfer of heat between the reaction that's taking place in the water and the solution, which is the water itself. So one is going to release energy and the other is going to absorb the energy. So sometimes that means the reaction might be releasing the heat and the solution might be absorbing the heat, or it could be the opposite of that. It could be the solution is releasing heat and the reaction is absorbing heat. So this concept here is one of the most difficult ones probably for us to figure out and work through as we do this thermochemistry stuff. But again, we'll do lots of practice with this before we get to the point where we're taking a quiz or a test over it. Okay, so I'm still going to do the same thing here. I'm still going to set my variables up down here. And then on this one, the main difference is when you're dissolving something in water is you're going to add those two masses together to get the total mass. So for this one, it says I have a 25.7 gram sample of sodium iodide. It dissolves in 80 grams of water. So to get my mass, I'm actually going to add those two together. And I'm only going to add them if it says it dissolves in something else. There's a different scenario if it doesn't dissolve, which we'll talk about in a second. So I'm going to take that 25.7 plus 80 to get my mass value for this. So that's going to be 105.7 grams. Okay, so that's my mass. The temperature rises from 20.5 degrees to 24.4 degrees. Okay, and again, delta T is final minus initial. So my final temperature was 24.4 degrees Celsius minus 20.5 degrees Celsius. So that is 3.9 degrees Celsius. I want to know Q for the process, so that's what I'm looking for. Then I also want to know whether it's endothermic or exothermic. Okay, so the C value, because this is happening in water, I can use that 4.18 joules per gram degrees Celsius. Okay, so anytime something's happening in water, like this one is, that's when I can use that 4.18 joules per gram degree Celsius that we looked at on that chart on the previous page. All right, so then I'm going to set this up. Q equals M C. And again, this C value, this is for water because it's dissolved in water. And then my delta T was 3.9 degrees Celsius. Okay, so when I multiply all that together, I get 1,723 joules. Okay, because if I look here, my grams is going to cancel out and my Celsius is going to cancel out, so I'm left with joules. That's where that joules value comes from. Okay, now what I have to think about here is my solution versus reaction. So this is happening, and sometimes it's helpful to draw a little visual here, so I'm going to draw this up here. So if this is my cup of water, when I am putting this sodium iodide into the water, the sodium iodide dissolving is my reaction. The water is where the thermometer is. Okay, so this is my thermometer. So the thermometer is in the solution. Okay, so the temperature of the solution is increasing. So when I solve for Q, because that temperature data comes from the water, this is Q for the solution. Okay, this says what is Q for the process. The process is the reaction. It's what's happening inside the water. So what I'm going to do here is I'm going to flip the sign, and Q for the reaction, which is the process, is going to be a negative 1,723 joules. Okay, and if we want to round to sig figs here, I'm going to go negative 1,720 joules. So that negative sign means it is exothermic. Because as that process, as that sodium iodide dissolves, it's releasing energy, which is why the temperature of the water increases. Okay, so this is something you might have to watch a couple times just because this is a little bit more confusing than that first example. The first example, those are super easy, but these next two can be a little more challenging. So again, when you dissolve something in water, you add the masses together. See if it's happening in water, we use a specific heat of water. And when we solve for Q, if it's happening in water, we're solving for Q of the solution because that's where our thermometer is. That's where our temperature comes from. So if the question is asking for Q of the reaction or the process, which it almost always will, we're going to flip the sign from whatever Q was. So if Q is positive, we're going to make Q of the reaction negative. If Q of the solution was negative, we're going to make Q of the reaction positive. And then that tells us whether our overall reaction was exothermic or endothermic. So in this case, again, it's exothermic because Q is negative. That process or that reaction released energy. Okay, our last type that we're going to look at today is placing a substance in water. So this is kind of similar to Q of one is the opposite of Q of the other. But this time, instead of having a reaction and a solution, we have two substances or two setups that we're setting equal to each other. So if you look at the formula for this, we have the formula for Q, mc delta T, equal to the opposite or the negative formula for Q, mc delta T. Because again, when energy is transferred, one is going to be taking it in, the other is going to be releasing it. This negative sign could be on either one. It doesn't always have to be on the second one, and in a second we'll talk about how you decide where to put the negative based on the information you're given here. Okay, so this happens when you put something in water and it doesn't dissolve. Okay, so usually this is going to be you're putting some kind of solid substance like a metal or a piece like a mineral or something that doesn't dissolve when you put it in water. So let's look at how we would set this one up. So this one says we have a 12.48 gram sample of an unknown metal. It's heated to 99 degrees Celsius. Then it's plunged into 50 grams of 25 degrees water. Okay, so I have a metal that's being put into water. So what I'm going to do is I'm going to do mc delta T equals mc delta T. Okay, now for now, I'm not going to assign one negative, one positive. I'm going to hold off on that for a minute. So what I'm going to do is I'm going to say, okay, this is the metal, this is the water. So over here, I'm going to make two lists for my variables. So I need an M for the metal, M for the water, C metal, C water, delta T metal, delta T water. Okay, and then we'll come back to our equation and figure out how we decide which side is negative. So my unknown metal is 12.48 grams, and it says it's heated to 99. Okay, we'll come back to that in a second. Then it's plunged into 50 grams of 25 degree water. temperature of the water rose to 28.1. Now, when you have a situation like this where you're putting a substance into water, the T final is going to be the same for both. So whatever the final temperature of the water is, that's also your final temperature of the metal, because they're coming to what we call thermal equilibrium. And you saw a little bit of that in one of those activities you did last week. Okay, so we're going to do, this is our final temperature. So this is T final. So to get our delta T for the metal, we're going to do 28.1, that's our final, minus initial, which was 99. So our delta T for the metal was negative 70.9 degrees Celsius. Okay, then on the other side, for the water, final was 28.1 minus 25. So our delta T for the water was 3.1 degrees Celsius. Okay, last thing is specific heat. So I'm solving for specific heat of the metal. So that's what I'm looking for. And then for my water, like we did in the last problem, specific heat of water is 4.18 joules per gram degrees Celsius. Okay, so now I'm going to plug these values in. So for my metal side, 12.48 grams. C is what I'm looking for. Delta T is negative 70.9 degrees Celsius. Other side, 50 times 4.18 times 3.1. Okay, now this is where you have to think about things and make sure you do this before you do any calculations. You have to assign this negative value to one of these two MC delta T's. The way you decide that is whichever one is releasing energy to the other one. So you could also look at it, whichever of the substances has a decrease in temperature. So in this case, the metal went from 99 to 28.1. So the metal lost energy. It decreased or released energy. Whereas the water went from 25 to 28. So it increased energy. So that means that the metal side is what I'm going to make negative because it released heat or released Q, however you want to think of that. So then this other side stays positive because it absorbed it. So it doesn't matter which side has the negative in terms of whether it's on the left side or the right side, but what does matter is you're going to assign the negative to the side that releases the energy. And again, usually if you're dealing with a metal and you're putting a metal into water, usually the side that's the metal is going to be the one that's negative. All right, so now we're going to do our math here. So this becomes 647.9. So this side ends up being 884.83. C. So then we're going to solve for C. So C ends up being 0.732, and it's still going to be joules per gram degrees Celsius. Okay, so that's how you would end up with your specific heat. And then you could use that if you wanted to go look up and see what metal that was. You could then do that. Okay, so again, this type of problem is when you put a substance in water and it doesn't dissolve. A lot of times it's going to be a metal when you're placing a metal into water. You set MC delta T equal to MC delta T, but you have to make one side negative to show that one side is releasing heat and the other side is absorbing it. Then you're going to solve for whatever's missing. So one type of problem with these, you're going to solve for C. There's others where it could potentially ask you to solve for a temperature. So if you have to solve for a temperature, they might give you the initial temperature and you have to solve for the final temperature. Those can get a little more involved, but we'll do some practice with those as we work through this. Okay, the last thing we want to look at today that's going to get us ready to do a lab is something called calorimetry. So calorimetry is the lab procedure that's used to measure the heat released or absorbed in a chemical or physical change. The simplest calorimetry experiment uses what's called a coffee cup calorimeter. So it uses basically styrofoam cups that are nested together with a lid. And then you put your thermometer into there. Sometimes you have a stirrer in there, depending on what it is that you're doing. And then the reaction takes place inside the styrofoam cup, and those styrofoam cups and the lid help it to retain heat. Because one of the biggest issues when you're doing experiments like this is there's so much heat lost to the surroundings. Sometimes it's hard to get good values. There's a more sophisticated way to do this, and something called a bomb calorimeter. That's what this device at the bottom is. We don't have access to these, but what happens here is it's a sealed container, and the sample inside is actually combusted, and there's a little different calculation that you would do for a bomb calorimeter, but that's another type of calorimetry, and we'll talk more about that in AP Chem. So when we do this, there's a lab that you're going to do on Explore Learning that's just kind of a straight up calorimetry lab. There's another lab that we're going to try to do with food calories, where you actually burn a substance and then see how much heat is released and see if you can compare the calories that you calculated to the calories on the bag and how much heat was lost when that happened. So if we're doing food calories, we talked about the other day how those are kilocalories or big calories. And 1 big calorie is equal to 1,000 little calories. And I talked a little bit about that in the notes, the previous set of notes. And then 1 little calorie is 4.18 joules. So if we are able to do the lab with the food item, then we'll talk through those calculations when we get there. But for what we're going to do next in the next Explore Learning lab, you're going to do some of those calculations where you're setting MC delta T equal to MC delta T. And again, I'll talk you through that when we get there. So work through your practice problems, and then we will come back together and review and see where everybody has questions.